Hello. When we talk about forces, it is important we talk about them in terms of their magnitude and direction because forces are vector quantities. When we talk about forces, sometimes it sounds abstract, but when we understand some other examples of vector quantities, becomes very easy to understand the concepts of forces, how they act on other bodies and several. So I'm making this video to let us understand how we describe forces, not just in terms of their magnitude, but also with direction. So when we talk about vector quantities, the example that comes to my mind right now is force, because that is relevant when we're discussing electric force, which is of interest to me. But you may be more conversant with displacement. So I'll start by using displacement as an example, then we move to forces. Displacement. We know about distance very well as a scalar quantity, but displacement is a vector quantity. What is the difference between displacement and what is the difference between displacement and distance? When I say a distance of 5 meters, a distance of 5 meters, when I start from a certain point A to another point B, 5 meters will mean the length of this line. But when I say a displacement of 5 meters, I'm talking about the line joining A and B. And it's not a complete information for me to say a displacement of 5 meters. Because when I'm talking about displacement, it is a vector quantity. I should mention both the magnitude and direction. That is, I should say maybe displacement 5 meters north, or 5 meters to the left, 5 meters downward. There should be an element of direction in that statement when talking about vectors. So I'll be talking about displacements. Displacement S equal to, let's say, 5 meters. This is not a complete information, but I can say a displacement of magnitude 5 meters. This is still acceptable, though it is not giving complete information. When I'm saying the magnitude of S is 5 meters, it may mean 5 meters. It may mean 5 meters. It may be anyhow 5 meters. When we say that a body travels from point A, it travels 3 meters to the right and travels 4 meters to the north to another point B. The distance that body has traveled is very straightforward. That is 3 plus 4. The distance traveled, then the distance A to B is equal to 7 meters. But what is the displacement from A to B? The displacement from A to B is the line joining A and B. The length of that line is the magnitude of the displacement, and the direction from A to B will be the direction to give us a full description. So when we say the body moves 3 meters to the right and 4 meters upwards, when we take this to be our 2D graph sheet, we are going to the right will mean x-axis, and moving upwards will mean y-axis. A convenient notation in vectors is to call the x-axis I and the y-axis j. It is widely used notation. And this displacement A to B can be described as 3I, because it moved 3 meters to the right, 3 meters to the right, that's 3I, and 4 meters upwards plus 4J meters. So you can see the distance is 7 meters, but the displacement is 3I, 4J meters. So the displacement S, let's call this S. So we can say that our S is equal to, if you let me use the same color, our displacement S is equal to 3I plus 4J meters. So let's play more with this displacement S. S 3I plus 4J meters. If the information I have originally is that there is a displacement S, which is 3I plus 4J meters, easily I can bring it out graphically to say that from a certain start point, 3 meters to the right, 4 meters upwards, and there will be, and the displacement, magnitude of this displacements will be this yellow line. And what is the magnitude of that yellow line? That magnitude of that yellow line is described as S magnitude. And solving the length of that yellow line using Pythagoras theorem is as good as we say S squared equal to 3 squared plus 4 squared. That's Pythagoras theorem. And S squared is equal to 9 plus 16. S squared is equal to 25. And S, which will be square root of both sides, is equal to 5 meters. So that means that the length of this line is 5 meters. So you can say the displacement is 5 meters. Fine, but that is not complete information about the displacement. When you say the displacement is 5 meters, you should also tell us the direction of that 5 meters. An easy way to talk about the direction, if you want to talk about in terms of 5 meters, is to specify the angle. the angle, let's call this angle theta. So you can talk about the saying 5 meters at certain angle. That is more complete information than just saying 5 meters. So we can describe our S as 3I plus 4J meters. We can also describe our S as to be equal to 5 meters and also talk about the angle theta. How do we determine this angle theta? The angle theta is when we know this is 4, this is 3, this is 4, this is 3, and this is the angle. Opposites, adjacent. We can use tangent of angles to determine tan theta. We know hypotenuse. We can use for arc cotangents or arc sine to determine what that theta is. Okay, let me bring back that our diagram. 3, 4, 5. Let me see. Five meters, 4 meters, 3 meters, and our angle theta. Theta maybe arctan 4/3 or arc sine 4/5 or arc cos 3/5. When you since this is 3 is from elementary school is the adjacent, 4 is opposite, and 5 is hypotenuse. So we can determine our theta easily. So let's go ahead and determine what is theta. I like sine of angle so much, so I'll say my theta is equal to arc sine 0.8, and arc sine 0.8 should be something around, if not that should be 56 or so. I think sine 60 should be 0.866. Yes, so sine 60 is 0.866. Then sine, then 0.8 should be something like about sine 56. 0.8 should be, so I'm not sure, so you can just confirm. Theta should be something around about 56 degrees. So it is convenient to say the displacement from that particular point A to the point B is saying S equal to 5 meters in direction 56 degrees. Sorry. 5 meters in direction 56 degrees. So as long as I've specified direction, and magnitude, then I'm talking about vectors. Another beautiful way to describe, instead of talking about 56 degrees, sometimes 56 degrees may not be convenient. Talking about is, let's go back to that our diagram where you travel 3 meters, 4 meters from A to B, and now knowing that the displacement has the magnitude 5 meters. And still talking about the displacement or the vector S to be equal to 3I plus 4J meter. The magnitude S is equal to, we've known that to be 5 meters. And now let's now talk about the unit vector of S. The unit vector of S is described as S caret. And the unit vector S is defined as the vector S divided by the magnitude of vector S. So when you look at the unit vector itself, the first thing that should come to your mind when you hear unit vector is to note that the magnitude is 1. So we can talk about our S. When we cross multiply this expression, we have our S. It can be defined in terms of the magnitude and that unit vector. So when we know our magnitude to be 5 meters, our magnitude of the displacement is 5 meters, then now we're interested in what will be the unit vector. So let's move ahead. I'm just writing the vector again, and S caret is equal to and that's as good as 3I plus 4J, all divided by 5. Since the magnitude of S is 5, and we still retain our value of S to be 3I plus 4J. 3I plus 4J, the unit is meter, and the magnitude 5 is also meter. So another property is to know that unit vectors have no unit. Their magnitude is 1, but they have no unit. So of course, M will cancel M to make it a unitless quantity. And now simplifying this further, we can say this is 3 over 5I plus 4 over 5J. And that is as good as saying 0.6I plus 0.8J. So this is our unit vector. S caret is 0.6I plus 0.8J. So that means that we can describe our vector S. We can describe our vector S to mean 5 meter times a unit vector, 0.6I plus 0.8J. And that's not a meter. So this is a good representation of the vector S, and this 5 meters times 0.6i plus 0.8j still means the same. This 5 meters still means the same magnitude, 5 meters, and direction 0.6i plus 0.8j. So let us check out what is 0.6i and 0.8j. Do they really mean a magnitude of 1? S caret equal to 0.6i plus 0.8j. What is the magnitude of S caret? That will be, let's call the magnitude, well, a good way is to say this is the magnitude, and that will mean 0.6 squared plus 0.8 squared, the square root of them all. And that will mean the square root of 0.36. 0.6 squared is 0.36, and 0.8 squared is 0.64. And when we add that together, we have 1. And square root of 1 is 1. So you can see the magnitude of S caret is 1. Since the magnitude of S caret is 1, that means that multiplying 0.6i, where's my pointer? That is multiplying 0.6i plus 0.8j, multiplying it to 5, does not affect the magnitude of S. The magnitude remains 5 meters, because the magnitude of 0.6i and 0.8j is 1, and 1 times 5 remains 5. So multiplying a particular magnitude with its unit vector makes no change, makes no difference to the value of that unit vector. Sorry, to the value of that vector rather. And fine, I've tried talking about 3 meters and 4 meters. It's just because we are more familiar with the unit meters. But when we're talking about newtons, there is no difference. We resolve them easily. When we say a force F 3I plus 4J newtons, what comes to my mind is that there is a particular body and a force of 3 newtons is acting to the right, and the force of 4 newtons is acting upwards. And from our elementary studies, we should note that if a force of 3 newtons is acting to the right and 4 newtons is acting upwards, that body, when the force of 3 newtons is acting to the right, we expect the body to move to the right. When the force of 4 newtons is acting upwards, we expect the body to move upwards. Now, when the force of 3 newtons is acting to the right, while another 4 newtons is acting upwards, then we should expect the body to move in a direction like this. So fine, the body will move in that direction, but what will be the magnitude of the force acting on the body? The magnitude will be the length of this red line. And how do we resolve that? and this is 3, well, we'll say this is 3 newtons, then we should also talk about another 3 newtons that is parallel to these 3 newtons. And these 4 newtons that is over here, that is acting upwards, we should also talk about another 4 newtons parallel to the existing 4 newtons that we have. And with that, our resultants, our F, will still be F will still be square root of 3 square plus 4 square, and that will be equal to 5 newtons. So our resultant will still be 5 newtons, and that resultant is as good as what is the magnitude. The magnitude of the force will still be 5 newtons, but we are also in some other ways we can describe the force as in terms of its magnitude and its direction. The unit vector would just tell us the direction. So, and like we've done before, our F caret will be 0.6i plus 0.8j, but this time around, okay, 0.6i and 0.8j. This would be the unit vectors. So when we are talking about 0.6i and 0.8j, we are talking about, since the length here is 5 meters, then the length of the length of the unit vector will be just something like this, just magnitude 1, just magnitude 1. And when the magnitude here to here is 1, then when we resolve this, there should be 0.6, and we'll resolve it to the horizontal component, that should be 0.8. So, and that is the meaning of a 0.6i plus 0.8j. This have a magnitude of 1. It has a magnitude of 1, but it is very useful, very helpful in specifying direction. So our force F, finally, our force F can be described. Let me write it in blue since we started with blue. Our force F can be described as 5 newtons times 0.6i plus 0.8j, all newtons. So now we have 2 versions of our forces. This is one, and this is another. They both mean the same. When you use the 5, when you expand these brackets, you would have exactly what we have here. But looking at this, I think I prefer this one, because looking at this at a glance, I know this is the magnitude, this is the direction. While looking at this, it's when it gives the same information, but this is somehow more friendly. So I hope with this, I call it short video now, I don't even know the length, I've been able to unveil some things about vectors, about forces, and talking about electric forces should be much easier than it used to be. Okay, bye.